In this video, we will prove these theorems listed in the problem section of Appendix B from the book Introduction to Algorithms, written by 4 authors commonly known by the acronym CLRS. You can pause the video and read the problem statements at your own pace. So, what does the problem statement say? So let's say we have a binary tree. So in this binary tree, we know that the number of vertices is 9. So we have to prove that we can bisect this tree into two parts by just removing one edge, so that the two parts formed have the number of nodes in them less than 3n by 4. So if we bisect it here, we will be left with this partition or this connected component with size of nodes equal to number of nodes in it equal to 5, and this other component, connected component, with number of nodes equal to 4. So both 5 and 4 are less than 6.75. Like this, we have to prove that in any generic n vertex binary tree, we can just remove one edge and the two parts will each have number of nodes less than or equal to 3n by 4. So that is what we have to prove in part A. Let us assume for now that the theorem A is true and look at theorem B. What does theorem B say? Theorem B says that if we want to change this constant from 3 by 4 to some other constant, can we reduce it further, or is it optimal? So let's take a binary tree with just two nodes. You know that by removing this edge, we can bifurcate into size n by 2 each, which are both less than or equal to 3n by 4. In case of 3 nodes, we can have two trees of different shapes. Here, in this case, we can bifurcate. In both the cases, we can bifurcate them into two parts with size n by 3 and 2n by 3. For this case, we can bifurcate it into n by 4 and 3n by 4. There is no other way. For the case of a node with a binary tree with total 4 nodes, and if the binary tree with 4 nodes is of this shape, then we can bifurcate into two sides and two trees n by 2 each. Okay, so the worst number you see is 3 by 4 only, so it cannot go below it. Assuming the A is true, although we have not proved it yet that 3n by 4 is okay, maybe this constant is more than 3 by 4, but so far we know that it definitely can't be less than 3 by 4. So part B is proved. Let's move on to the next section. Let's come back to part A. In part A, we have to partition the vertices of any n vertex binary tree into two sets A and B, such that cardinality of A is less than or equal to 3n by 4 and cardinality of B is less than or equal to 3n by 4 by removing a single edge. So if we have to divide the tree into two such parts, then definitely the A has to be greater than or equal to n by 4 as well. If B has to be less than or equal to 3n by 4, then A has to be greater than or equal to n by 4 as well. So let's try to find solution to this. Let's assume that there is a tree with root node n. Root node with size n. By size I mean the total number of vertices in the subtree rooted here. Total number of vertices in the subtree rooted at n. Subtree rooted at the top node is n, and the same number here is L and S, such that L plus S plus 1 is equal to n, which is kind of obvious. And assume without loss of generality that L is larger than S. L is for larger and S is for smaller. So let's say the left subtree is larger, and that would mean that L will always be greater than n minus 1 by 2, because we have already assumed that L is greater than S. So if we divide the total of L plus S by 2, the minimum value of L will be that only. So from this we can prove that L will always be greater than n by 3 for n greater than equal to 3. You can follow through these steps and see for yourself that L will always be greater than n by 3 for n greater than equal to 3. What happens when n is less than 3? When n is less than 3, let's assume that n is 2. What will happen if n is 2? If n is 2, then obviously there will be only one child node below n. So this will be the shape of that tree, and n will be 2 and L will be 1. And in this case L is actually equal to n by 2, which is greater than n by 3. So we know that for all cases wherever n is greater than equal to 2, L is always greater than equal to n by 3. We have proved that. So what we have proved so far is, when going down the path of the larger child from a parent node, the number of total nodes in the subtree rooted at the current node can decrease maximum by a factor of 3. So the total number here, if it is n, then and we move down the path of larger subtree, then this number n will decrease maximum by a factor of 3. It cannot decrease more than by a factor of 3. So it cannot go below n by 3. That's what we have proved so far. Now to prove part A, let's assume that we are traversing down the tree, and we are traversing down from a node with size x. By size I mean number of all the nodes in the subtree rooted at that node. So if we are traversing down from x to L, L is the larger subtree, such that x is greater than 3n by 4. We haven't found a node which is bigger than 3n by 4. So we are traversing down x from x to L. So there can be two cases. One is where L is greater than 3n by 4. Here x is not necessarily the root node of the binary tree we started with. We are just traveling down the tree randomly, and this x is just one of the nodes in that tree. So when we move from x to L, there can be two cases. One is L greater than 3n by 4. In that case, we will move further down the node L in the direction of larger subtree of L. Okay. In case 2, this L can be less than or equal to 3n by 4. And again, x is assumed here to be more than 3n by 4. If x is more than 3n by 4, then as we know that L is always greater than or equal to x by 3, L will also be greater than or equal to n by 4, as x is greater than 3n by 4. So we know that whenever we will move from a node above 3n by 4 to a node below 3n by 4, it will also be greater than or equal to n by 4. So if we just remove that edge between x and L, whenever case 2 appears, we will remove the edge between x and L, and we will get the two partitions we need. Let's move on to prove part C. What does part C say? Before that, let's try to understand this paragraph. This paragraph says that we can bisect the tree by removing a small number of edges. For example, in this tree, we can remove this edge, we can remove this edge, we can remove this edge, and we can remove this edge. And by doing so, we can divide this whole tree into some connected components. One will be this one, another one will be this one, and there is this one, then there is this one, and there is this one. So by removing some edges, we can divide the tree into multiple connected components, and then we can group all the connected components into two sets such that each set has a size almost equal to n by 2, or in other words, one set has a size equal to floor of n by 2 and the other set has a size equal to ceiling of n by 2. In part C, we have to prove that we can do so in maximum order of log n edge removals. So now to prove C, we will use this fact that any binary tree can be divided into two parts by removing one edge, such that each of the two parts are of size between n by 4 and 3n by 4, both inclusive. So we'll follow this routine which is mentioned here, pseudocode which is mentioned here, and you can pause the video and go through all the steps of this pseudocode. And now that you have gone through it, let's analyze the number of times we need to remove the edges. If n is the number of edges, every time we remove one edge, we are left with a smaller tree which can be of size maximum 3n by 4. Okay, so how many times we need to multiply n by 3 by 4 so that it becomes 1? That is the number of edges we need to remove maximum. The number will be equal to log n base 4 by 3. This can be written as big O of log n. Hence proved. Bob is your uncle.